First thing I'm going to review is special factoring and special multiplication patterns for polynomials. The first special factoring patterns we have are our perfect square patterns. So if I have a squared plus 2ab plus b squared, I have two numbers that are squared plus the square roots of them times the product of 2. This is ended up to a plus b times a minus b. I don't memorize it that way. I say it's the square root of the, actually those are both a plus b. It's the square root of the first, square root of the last, copy the sign, all squared. For example, if I have 4x squared, got a plus 9 here, plus 12x. What I look at is that a perfect square? Yes. Is that a perfect square? Yes. So what do? I'll try it to see if it's a perfect square pattern by taking the square root of 4x squared, which is 2x. I take the square root of 9, which is 3. I copy the sign, put the all squared, and then I check to see if the answer is correct by multiplying 3 times 2x, which is 6x, times 2, which is 12x, and I do get the middle number. The same thing would work if I had a minus sign. So x squared is a perfect square, 9 is a perfect square, so I'm going to try the perfect square pattern. I'm going to take the square root of the first, which is x, square root of the which is 3, copy the sign, negative, all squared, and I'm going to try by multiplying out to make sure the middle term is correct. Negative 3 times x is negative 3x, times 2 is negative 6x. So this pattern works for both perfect squares that are plus or minus in the middle term. And I want you guys to realize that this doesn't say it's just squared, it means it's something squared. And here I have the expression x to the fourth plus 4x squared plus 4. X to the fourth is something squared. Well, what is it? Squared? Well, it's x squared. What is the square root of 4? 2. Copy the sign, all squared. And let's see if this works. Well, 2 times 2 is 4, times x squared is 4x squared. So I do get the middle term. So I want you to realize that, hey, you can have things that aren't just necessarily x squareds in here. Later on this year, when we work on trigonometry, you may see expressions like the sine squared of theta plus 4 times the sine of theta plus 4, and you will still use the same pattern to factor this in order to solve. So in this case, this is something squared. Well, the square root of sine squared is sine. The square root of 4 is 2. Copy the sign, all squared, and check that the middle product is right. 2 times 2 is 4, times the sine of theta would be 4 sine theta. So remember, it's a pattern, and the pattern is better in words. I have something squared for the first term, something squared for the last term. If I have those two things, I'm going to try my pattern. Square root of the first, square root of the last, copy the sign, all squared. And then I'm going to check that if I were to FOIL it out, I'd get the correct middle term. Our next pattern is called the difference of squares pattern. And again, you can recognize it by having two things that are squared with a minus sign in between them. That's why it's called the difference of squares pattern. And in that case, it's the square root of the first plus square root of the last times square root of the first minus square root of the last is our factors. Examples, 4x squared minus 9. 4x squared is a perfect square. 9 is a perfect square with a minus sign in between the two. So my answer would be 2x plus 3 times 2x minus 3. So that's how we get the difference of square pattern there. I also want you to realize that because we don't necessarily have to deal with numbers that are perfect squares, this pattern also works for any time that you have something squared minus a number. Okay, if I have something squared minus a number, for example, 5x squared minus, let's go 6. Well, what's the square root of 5x squared? Well, it's the square root of 5 times x. What's the square root of 6? Well, it's the square root of 6. The square root of 5x minus the square root of 6. In most cases that you're going to deal with, you're going to have integers that you're going to be able to do perfect squares with. But I want you to realize that this pattern right here works even if the coefficients are not perfect squares. You do need something that you can take the square root of. Well, let's just do x minus 4. Well, what's the square root of x? It's the square root of x plus the square root of 4, which is 2, times the square root of x minus 2. Now, I'll tell you right now that this is an acceptable factorization of this, but in 9 times out of 10, our only answer that we would have here would be x equals 4 because we are already linear. Where this would come into play is if you had the problem x minus 4 over the square root of x minus 2. Here you should realize that if you actually do the division here, our final answer, because x minus 4 can be factored in x, square root of x plus 2 times the square root of x minus 2, the x minus 2's would cancel, and your final answer would be the square root of x plus 2. So there are reasons that you'd want to be able to do problems like this and be able to factor them. So those are our patterns with quadratic type polynomials. The next patterns I want to talk about are for sum or difference of cubes. So if I have a cubed plus b cubed, or a cubed minus b cubed, what sum or difference of cubes turns into a binomial times a trinomial. The numbers that I put in for the sum or difference are going to be the same. The only difference is going to be the signs that I use. And the way I get my binomial is just take the cube root of the first term, cube root of the last term. Then the first term here in the trinomial is this first term squared. The last term is the last term squared. The middle term is the first times the last. And that's the same thing for the difference. So what I want you to realize is that this pattern is a little bit different than if I were to FOIL something out where it's 2 times the product for something squared. This is just the product. Now, here's how the signs go. We copy the sign. We change it. Always positive. Copy the sign. Change it. Always positive. One thing I want to tell you about that if you get one of these answers that are on the right-hand side by factoring, and you want to check to see if you actually got the right answer, you could take your answer and multiply it back out, and you should get what you started with. So let's do some examples of sum and difference of cubes. I'm going to have 8x cubed minus 27. 8's a perfect cube, 3's a perfect, x cubed's a perfect cube, And 27 is a perfect cube. So it's the cube root of the first, which would be 2x. Cube root of the last, which would be 3. First term squared, which is 4x squared. Last term squared, which is 9. Middle term is 2x times 3, which is 6x. Copy the sign, change it, always positive. So this is a linear factor, which is something that you can plot. You get x equals a positive 3/2. This will never factor. This is one of those quadratics that has no real solutions. 100% of the time, these two factors are quadratics with no real solutions. You should have a goal that if it's a perfect square pattern, sum or difference of squares or the sum or difference of cubes, that you should be able to get 100% of those types of questions correct. The other thing I want you to realize is that if you have these patterns, that you can go back to the original polynomial. The one in particular that we're going to use a lot is this difference of squares pattern. And that's how we're going to get rid of square roots that are just floating around randomly in our problem. And just as a preview, we do not like having square roots in the denominators of fractions. So I want to get rid of this square root in the denominator of the fraction. Well, it would be really nice if that wasn't a square root. Well, the square root of something squared doesn't have the square root anymore. So the way we get rid of those in the denominator of our fractions, if it's a binomial square root, we will multiply by its conjugate. And you should notice that I have that difference of square pattern. I have a number plus a number times a number minus the same number there. So the top would just give me the 1 plus the square root of 3. On the bottom, I'd end up with the first term squared minus the last term squared. Square root of 3 squared is 3. Final answer would be negative 2 on the bottom. So I put the negative out front, 1 plus the square root of 3. And that's how we would like our final answer to show up. So that's just a preview. Again, when we're working with exponents, just a reminder that we can do that.